Next we will move to the next topic. It's a TCP/IP model. After the OSI model, new model was proposed, which is a TCP/IP model, in which only 4 layers were used. The functions of few of the layers in the OSI model were combined, and they gave birth to a TCP/IP model. In the TCP/IP model, we have only 4 layers. The data link and physical layer combined to form the host to network layer. The third layer remains the same, it's a network or the internet layer where the routing protocols and the routing algorithms would run. Fourth layer is the transport layer, again that remains the same, where we'll have the TCP or UDP coming in. And finally, the session presentation application got combined into one layer, that is REST application. This is what the TCP/IP model is. And the functionality remains the same as I explained here. The only thing that will change is the functions are combined into one layer rather than, for example, 3 in case of session presentation application. Now we will explore more about the layer 4 of the OSI model. On the layer 4 we have two well-known protocols, TCP and UDP. TCP is transmission control protocol, UDP stands for user data account protocol. So both operate a transport layer, yes, and TCP is connection oriented and UDP is connection less. What do we mean by this is that whenever communication between two hosts takes place via TCP protocol, the communication parameters will be negotiated in advance and later on the communication would start. On the other hand, in case of UDP, the communication would start directly without any negotiations with the other end, and no retransmissions of low control would be given for UDP. What are retransmissions and how do we achieve them? We'll see them in the succeeding slides. So applications, for example, TCP, where you need reliable things like file transfers, email, etc. For example, in email you are writing a text, so the text should appear similar to the receiving entity. It should not be like A has become Z or B has become C. So for those applications where we need high reliability, we will use TCP, and for real-time applications we will use UDP. The reason is, in real-time applications like voice and video, we don't have time to retransmit the data. For example, say we are watching a live cricket match, and the multicast stream is being transmitted on the television, and suddenly for 2 or 3 seconds, if we get a flicker or we get some loss of signal, then for the next 10 seconds, if we see again what was lost, and that is actually not causing the live effect, because we are seeing something now which was past. So if this effect goes on cumulative, then that is not something which we want in case of voice and video. So in case of voice and video, because it's real time, the only thing that we can ensure is the loss should be minimum, and in case of failures, the resiliency should be very high. So the traffic should immediately switch over to some another path and start working. So UDP is used for real-time applications where slight loss may be tolerable. Now we'll discuss about the detailed operation of TCP. So in TCP there are few phases. We'll discuss them step by step. First is the connection establishment. So in connection establishment, first of all in TCP, we always have two elements. One will be a client and another will be a server. And the communication will be initiated always by client. So in connection establishment, which is the first phase, we'll have three-way handshake. That is, the client will send a SYN message to the server, and this SYN packet will contain sequence number X. When the server receives it, server will send a SYNAC back to the client, but this time what it will do is, it will use this sequence number to generate an acknowledgement number, which will be X plus 1. and generates its own random sequence number, say y. Now what was the significance of this x plus 1 is that the server is telling the client that I have received your packet with sequence number x, hence the acknowledgement number x plus 1. Now when the client receives the packet, client again generates an acknowledgement back to the server with the same logic, that is, server has sent me sequence number y, so I will generate an acknowledgement number y plus 1, letting know the server that I have received your packet with sequence number y. And again it generates its own sequence number x plus 1. It will increment this original sequence number. It was x, now it's x plus 1. So if these three-way handshake is complete, the TCP session is established and it's open, and the session can enter into data transfer phase. So what happens in data transfer phase, and how do we detect the errors, and how do we detect the losses and retransmission, that we'll check later. Now the third stage, that is connection termination, which is a four-way handshake. In connection termination, the initiator will send a FIN packet to the receiver. Whoever wants to finish the communication, that is the sender, will send a FIN packet to the receiver. Receiver will acknowledge it and also send a FIN from its side, and the initiator will again acknowledge it. Hence it is called as four-way handshake. Because in this case we are depending on the other end as well to initiate FIN, and then we can acknowledge. So this is the first and the third stage, you can say. First stage should be connection establishment, then data transfer, and then connection termination. So we'll discuss the data transfer now. So in data transfer phase, of course the actual data is being transmitted in this phase. Rest is signaling. The connection establishment and termination is the TCP signaling. In ordered data transfer takes place in TCP. What do I mean by that is, using these sequence numbers that we discussed in the establishment phase, data transfer that is happening between the sender and the receiver can be reordered at the receiving end if the packets are not received in order. For example, if I have packets from 1 to 100 and I have sent those packets from the sender to receiver, and in that case, for example, let's say 1 to 50 packets were received and 51 to 60 packets were not received, and 70 to 100 were received, and in the end 61 to 70 those packets are received. So what has happened? Missequencing of packets was occurred. So this resequencing has to be performed at the receiving end. So it's ordered data transfer. The data transfer has to be in proper sequence, proper order. Next, yes, retransmission of lost packet. So how do we know whether a packet has lost? Let me see the diagram. Okay, so for retransmission of lost packet, let's see. We will depend on the sequence numbers. So we have a sender. Let's say we have a sender and we have a receiver. Okay. Now let's say for first instance, the sender is sending packets with okay, so duplicate acknowledgement based and timeout. So sequence number is X. Sender has sent packet with sequence number X. Receiver has acknowledged that packet with by sending acknowledgement number X plus 1. Okay, so this is now the acknowledgement number, that will be X plus 1. Next, sender again sends the next tree. Let me make it clear. This should be the sequence number. Should be the sequence number. This is the acknowledgement. Okay. So if a sender doesn't receive an acknowledgement for the sequence, for example x plus 1, which it would be sending next, then there are two mechanisms to conclude whether retransmission has to be done or not. So let's say, for example, one more packet has been sent by the sender. This time the sequence number would be x plus 1, and the sender is waiting for an acknowledgement to be received from the receiver. It's waiting for acknowledgement. So now if this acknowledgement is not received, then there will be a certain time limit that the center will a timer that the center will set. If the timer expires, then the center will understand that the receiver has not received the packet and hence unable to acknowledge within the set timer. So I will have to retransmit this frame, that is this data segment at sequence number x plus 1. So the center will again retransmit the data segment, that is x plus 1. And in this case, if the receiver receives it, then it will again send back the acknowledgement. So this is how the retransmission occurs in TCP. And when it will send the acknowledgement, it will send acknowledgement number x plus 2, and of course the receiver will have its own sequence numbers as well, which the sender has to acknowledge. But we are discussing it only from the perspective of sender. Sender sends sequence number x, acknowledges with x plus 1. Next, sender sends sequence number x plus 1, which the receiver doesn't receive, and hence sender doesn't get an acknowledgement and the timer expires. That makes sender aware that I need to retransmit the sequence x plus 1 again, and hence it retransmits that sequence again, as here and here. So this is the acknowledgement. The last one is the acknowledgement received, that yes, I received x plus 1. The upper one is the retransmission of the data segment. So this was the timeout based retransmission that we discussed. Now what is duplicate acknowledgement based retransmission? So let's clear this up for a minute. In duplicate acknowledgement based retransmission, what will happen is the receiver will send acknowledgement for the lost data segment twice. So that will make the sender realize that okay, this is the data segment that I need to transmit again. So what do I mean is, for example, let's say here, okay, so let's say here we transmit sequence x. Let's say the window size is 1. I will tell you what's window size in the next slide.